Can the online students hear me? All right, we are done with the process abstraction, and now we are going to start looking at the memory system, the memory hierarchy, and the storage hierarchy. Before we go on to virtualize it the same way we virtualize the CPU, we enabled the execution of different applications, programs. Multiple users can share the CPU using exceptional control flow and context switches. Okay, before we do the same with the memory system, before we let our memory system be shared by different applications, and before we create that illusion, I want you to understand how memory devices, how storage devices work a little bit. Now, this is important because historically, the device characteristics, disk storage, solid state drives, and the difference between how these input-output devices work and how the memory system overall works and how RAM works has informed the design of software around us. And so once we understand the characteristics of devices, we will be able to write better software, well-performing software that is tailored to some of these ideas in the memory and storage hierarchy that are enduring. These are not going away anytime soon. Okay, let's start with RAM, random access memory. Physical memory, there are two types: static random access memory and dynamic random access memory. What we use as physical memory in our systems is DRAM, dynamic random access memory. The DRAM package looks like this. Each of these is a chip. Each of these is a chip, and there are chips on both sides. Okay, and this is what you plug into your motherboard or any other system. And we call it a DIMM. By the way, the slides are online if anyone wants to annotate. Or dual inline memory module. Okay, and there are many of these. We use many of these to expand the capacity of our physical memory or our memory system. Static RAM is much faster, but it is much more expensive. You can think of these static RAM cell as a flip-flop. A flip-flop takes up 6 or more transistors. It takes up a lot more area, but it is very, very fast. Unfortunately, it's also very expensive. We will keep seeing this trade-off in memory and storage system. Some technologies are faster but expensive. Others are cheaper but slow.
Yeah, so where will you find static RAM used normally? Where will you find dynamic RAM used normally?
Dynamic RAM is typically, that is your physical memory. That is your main memory. And static RAM is your register file. And we use it in some other ways. So anything that is close to the processor, close to the CPU, like a register file, any register, we'll look into caches in a little bit. We use this static RAM technology because it is really fast. And outside the processor, when we connect the processor to physical memory, we use DRAM. This is the view of RAM that we would like to have. We can address an individual byte. Each of these bytes have a number, have an address, 0, 1, 2, 3, 4, 5, 6, 7. And the reason we call it a RAM or random access memory is doesn't matter which byte you want to access, it takes the same amount of time. And we will see that the other devices, the input-output devices, storage devices, disk, they don't have this feature. They don't have this quality. This is why we call it RAM. No matter where you go, you give it an address and it spits out a byte in the same amount of time, about 50 nanoseconds today for DRAM. And we will refine this view shortly. There's a few things that we have done over the years that sometimes could lead to different latencies for different types of accesses. But those are optimizations that are that may or may not be there. This is the view of RAM that we would like to have. You give it an address, it spits out whatever is stored at that address. And doesn't matter which address it is, it takes the same amount of time. Random access memory. Sometimes you might see, so we don't access typically, we don't bring bytes from memory. We try to bring a word, 4 bytes or 8 bytes, because these are the objects we use in our programs, integers, shorts, longs. Okay, so word addresses go from 0, 1, 2, 3, 4, and byte addresses 0, 1, 2, 3, 4, 5, 6, 7. So these 4 bytes are part of this word. This is showing the data, and this is showing the addresses. So transistors per bit, this is one way to measure, quantify the area of different technologies. So SRAM, about 4 to 6 transistors, and DRAM, 1 transistor. DRAM is about 10 times slower than SRAM. So that's why your register file, your registers, small register file, is 10 times faster than going to memory outside the processor. DRAM actually uses, if you can refresh your knowledge of physics, a capacitor to store charge. And capacitors lose information over time. They lose charge over time. SRAM has, the SRAM cell has flip-flops, and there's a feedback loop, and there's a constant flow of current, and you don't lose charge over time. So that's why DRAM, we need to refresh from time to time. Every 10 millisecond, every 20 millisecond, we need to refresh those capacitors. So there's a disadvantage of DRAM. It needs to be refreshed all the time. For the same reason, because if there's a particle strike, alpha particle strike, or if it's working in an environment where there's a lot of noise, DRAM needs special EDC support. EDC is error detection and correction. We typically don't need such support for SRAM. So DRAM is used for main memory, frame buffers, which is something in your monitor, and cache memories. We will discuss caches. So caches, because DRAM is so slow, over the years, what system designers have done, they have placed a small amount of cache memory, SRAM, very close to the processor, about few megabytes, right? And DRAM, main memory outside the CPU, is many, many, many gigabytes. DRAM and SRAM are volatile memories. When you turn off the power, you lose information. There is no longer the charge. The charge is no longer there. In the case of SRAM, it needs constant supply of voltage. If there is no voltage, if you turn off the machine, so you have to be very careful when writing software. If there's a crash at any time and you have useful information in SRAM and DRAM, main memory or your CPU, you need to decide when things come back live, what to do. So this is one aspect of software design that is important. Non-volatile memories retain information beyond shutdown. When you turn off the power, whatever is stored in your disk drive or solid state drive is still there. We call it, these technologies are persistent. They retain information beyond a power off. So classically, we call them read-only memories. This is just a historical thing. You can actually read and write non-volatile memories. This is just something we carry from the past. ROM is programmed during production. I'm just going to quickly go through these. It's not really. ROM is programmed in the factory only once. PROM has a quartz window. You can pass light on the storage cells to reprogram them. The problem is, for PROM, you need special circuitry. You need to go somewhere to, or you need special equipment to program it. EPROM is something that you can put on your motherboard, and it's electrically, sorry, that's EPROM. Okay, ROM is, it is programmed during production. PROM is programmed once. You cannot program it again. EPROM is, you need special equipment, and electronic erase capability is where you can actually put that on your integrated circuit and you can erase it using software. And then there is flash memory that we'll look at in detail. You can actually partially erase certain blocks. So the distinction between ROM and PROM is a little bit blurred. For EPROM, you need special equipment. For electronic erasable PROM, you can do it on your circuit board, and we'll talk about flash. So what you store inside these ROM devices is called firmware. This is, startup code, stuff like that. So let's look at how CPU accesses anything stored in main memory. Suppose I have a load operation like this. So this is my address, and this is my destination. So what I have here is, this is my CPU chip. And there are two buses here. Bus is just a collection of wires. It's a channel through which different components communicate. So there's a system bus. This is a general view of a system. Different systems may use different terminology for these buses. So there's a system bus and there's a memory bus, and there's an I/O bridge that translates whatever CPU is requesting into signals for the memory bus. And we'll see in a little bit why we need the I/O bridge when we connect I/O devices. So I/O bridge also contains the memory controller. And that controller actually translates the signals coming from the CPU's bus interface and sends them to main memory. Okay, so we want to load whatever is at address A into RAX. And this is our register file. This is RAX. So we give the IO bridge, the memory controller inside the IO bridge translates, takes the address, sends it to memory, address A, memory returns X, and X is stored back in the register file. Now, there are three things I want you to note here, and this will distinguish the behavior of input-output devices and memory. First of all, CPU has kind of a direct access to memory. There is no intervening layer. So it sends the address to the memory controller, and it reads whatever is stored at a specific location in memory. So we call it direct access, and this will become clear in a little bit. There are the storage devices, disks, SSDs. The CPU cannot communicate directly. It has to request someone, and that someone is a controller, and that controller has to place the contents of whatever the CPU is looking for somewhere, and we'll see that in a little bit. So direct access is one thing. Byte addressability is another thing. I don't know if I spelled it correctly. The CPU can access individual bytes that are stored in RAM. So direct access also means that the CPU can use load, store, move instructions to access the contents of memory, to read the contents of memory, or to write the contents, write something to memory. So byte addressability should be obvious. This is how RAM works. Every byte has an address, and the CPU can bring in its register file any byte it wants. And we can use normal load, store, if you're on ARM or if you're on x86, move instructions to directly access what is in memory. There is no other sort of translation going on. And it will become clear soon what I mean by translation. Okay, similarly, a store operation, the CPU wants to store Y. It places the address on the system bus. The IO bridge translates it into, places the address on the memory bus, and eventually we write Y in memory. Okay, so we call this direct access. There is not a lot going on between the CPU and memory, except for the address and control information going between the wires and the buses. All right, so we want to see now, so far we know how the CPU accesses RAM or memory.
What stage is the address get translated from the virtual address to the real?
Okay, we'll talk about virtual memory in the next lecture, but that translation happens inside the CPU. Once the address is on the bus, it's a physical address. The RAM doesn't know anything about virtual physical. It has no clue. This translation is something that operating system and the CPU are doing together, right? They know that we have to give this illusion. In fact, it's just the operating system who gives this illusion of multiple users using physical memory. Physical memory itself doesn't know anything about, right, what is virtual, what is physical. It's just an array of bytes. So that translation happens here, not even here. But we'll do this next week. Okay, so far we know how the CPU accesses memory, and we can write assembly or C, and those instructions can directly access the contents of memory. Now, before we see how IO devices, storage devices access are accessed, we need to pick one technology that we understand. And here is your classical disk drive. Okay, they're not going away anytime soon. So it's not a bad idea to learn how they work. First of all, this device, so I will say input-output device. What I mean is any kind of storage device, sorry. When I say storage device, I mean disk or SSD, solid state drive. So here's a device with moving parts. Right away, there's a huge difference between RAM and disk. It has moving parts. And we will see that it cannot give you this same, it doesn't have the same property that you access any random location and it takes the same amount of time. And partly it's due to how it is made. There's an actuator that moves this arm in this direction along the radial axis, and these platters rotate, okay? So a platter has two surfaces, and on both surfaces, there is recording material where we record our bits, our storage information. And there's a spindle that actually rotates these platters, okay? So arm movement, remember, is in this direction. Sorry, this is the axis along which the arm moves. The actuator moves the arm in this direction, and the platters rotate actually in this direction. So by rotating the platters and the combination of arm movement and the platter rotation, we can store and retrieve a lot of information. There is a head at the end of the arm that actually senses whatever bits are stored. Okay, so the geometry of the disk is, it consists of platters. Each platter has two surfaces, and each surface consists of concentric rings called tracks. So there's a lot of tracks. All these are tracks on each side of the platter, right? And each track is further divided into sectors, and there are gaps between sectors. Platters, two surfaces on each platter. Each platter has a number of tracks, innermost to outermost, and each track is divided into a bunch of sectors. Each sector is typically 512 bytes. And you cannot access a single byte from disk drive the same way you access it from RAM. When you ask a disk drive, give me something at that address, it gives you the entire 512 bytes. So already there's a big difference between RAM and storage devices, storage device. Minimum information that you can access, the minimum granularity is typically 512 bytes. Today you can find 1 kilobyte or more. Okay, so if you look at all the different platters, there are multiple platters in a disk drive because you want more capacity in a single drive. Each side has tracks. Each surface, 0, surface 1, surface 2, surface 3. And you can look at, if you cut a slice through these platters, you can see that all the tracks that are equidistant from the spindle form a cylinder. Okay, let's take a moment. Do you see any waste in this geometry? So there are multiple tracks, and a cylinder is collection of tracks on all surfaces that are equidistant from the spindle. So all the tracks here on both sides They form a cylinder. And each track is divided into sectors, right? There are many sectors on each track. What here is, there's a lot of waste here. Why is that? If I tell you that no matter where the track is, it has the same number of sectors. Right. So the innermost tracks are much more denser. The gaps are really small. But as you go out, if you don't change the number of sectors, the gaps are much bigger, right? And when you say, you know, I'm formatting my disk, these gaps are filled with special information. This is what formatting does. And then you lose all the existing information. Okay. So the reason we are doing this is not to understand how mechanical devices. There are some interesting lessons here. The difference between RAM, I want you to think about this. Keep this in mind, how RAM works and how is this different? And the way software sees these devices is different. And the way we write software, when we write low-level software, we have to know these things. If we treat everything as RAM, we will be writing very inefficient software. Okay, so capacity is the number of bits you can store. I just want to go through them quickly. Recording density is the number of bits per inch. These are all metrics that quantify density, how many bits you can squeeze per inch. And over the years, the recording materials have improved, the technology has improved, and we can now record more bits per inch. That's all this slide is saying. Okay, so to remove this, to get over this inefficiency, today we divide the cylinders into disjoint recording zones, and within each zone, all the tracks have the same number of sectors, and the number of sectors are defined by the innermost, how many you can squeeze in the innermost track. And then outer tracks now have more sectors than inner tracks. So this is what they did a few years ago, zoning, where you don't need this uniformity of having the same number of same number of sectors on every track. You divide the tracks into zones, and each zone, all the tracks in a zone has the same number of sectors. And this makes it easy to manage and to know when you access a specific track on disk, how many sectors does it have? So there is this, the geometry is a little bit more complicated with recording zones. Okay, so capacity now is defined by the number of bytes in each sector. I already told you this is typically 512. Average number of sectors per track, this depends on the technology. Number of tracks per surface, this also depends on the technology, how far apart you want the tracks to be. How many surfaces per platter? And number of platters per disk is between 5 to 8, something like that. And when you multiply all of this, you get disk capacity. So I was saying, now let's see how the operation, and this will clarify further the differences between RAM and disk. Okay, so the disk surface spins at a fixed rotational rate. So now I'm going to animate just, you know, how the spindle spins the platters. So, so the rotation, remember, there is a rotation. One aspect of accessing a disk is rotation, rotational latency. And now, by moving the arm here, you should have this picture in your head. You can access any sector by using the combination of rotation and the actuator moving the arm. So now I'm going to demonstrate the arm movement. All right. So now you know you can access any track by rotation or arm movement. If you want to go to a different track, which is important, rotation or arm movement? And if you want to go to a specific sector on a track, what is important? Rotation. Okay? This is important. So the read-write head is attached to the end of the arm and flies over the disk in a thin cushion of air. And the underlying technology actually is really, really interesting. It's really cheap. Disks are really cheap, but the technology inside the airtight package, and there's a micron level distance between the head and the recording material. Anyway, let's not get into all of that. Okay, so there's one arm. There are multiple heads, 2 heads per platter. And they all move together in a cylinder. If we look at the disk structure, these are the tracks. These are our sectors. All right, let's say the head is at this position, and we want to access, and the platters rotate counterclockwise, and we want to access the blue sector. We want to access the blue sector. So the head is in a very nice position. So this application, if the head is in this position and the application wants to access something on that sector, the application is really lucky, because no head movement, no arm movement, simply is transfer. Simply a transfer. Now imagine the application then says, hey, I want something on the red sector. Now this is a random access, okay? This is random access. In the case of RAM, the application will see the same latency for accessing the blue sector and the red sector. What is the first thing that needs to happen here? Arm movement or rotation? Arm moves, and we call it a seek. And you will see system calls. The arm movement for a specific track is called a seek operation. The next thing that needs to happen is rotation. And the next thing is the transfer. Once the head is, the first bit arrives underneath the head, it takes some time for the transfer to take place. This is by no means a random access device. Call it whatever you want, it is not a random access device. There are things moving, the arm is moving, depending on where the head is at this point and where the next access, what the application requests, there is either going to be arm movement or rotation or both, and transfer and all that. You cannot predict the behavior of this device. So there are 3 components. How long does it take to access a RAM? 50 nanoseconds, done. It's not the same here. Transfer time, seek time, rotational latency. Okay, 3 components of a disk access. Seek time is typically between 3 to 9 milliseconds. Millisecond is 1,000th of a second.
The maximum seek time and rotation,
You can't do both actions at the same. You don't do them. Now, I don't know if there's technology to do that, but this today don't do that.
all the patterns are independent from each other, or they are rotated all together based on the.
They rotate together because the spindle is connecting all of them. And we can exploit that to store files, information in such a way that everything is placed on a cylinder.
The arm
and put more heads on one arm for each strap.
Okay, so now we are talking about, yeah, we can talk about, yes, okay. These are very sensitive. The head movement, everything is very sensitive. And the rotational latency, okay, I'll have you look at these formulas on your own. But the average rotational latency here is 1 over RPM. RPM is revolutions per minute. And this is basically minutes per revolution. And this is what you want. Minutes, how many minutes it takes to rotate the disk. And then they divide it by 2 to get the average. This is just minimum plus maximum over 2. Arithmetic mean. The minimum rotational latency is 0. The head is nicely aligned with whatever you want. Maximum is you have to rotate the whole thing. So whenever you have a situation like this, you take the arithmetic mean as min plus max over 2. So that's why we divide it by 2. And 1 over RPM is, typically we know the RPM, revolutions per minute. RPM is revolutions per minute. If we know the RPM, we can do, the inverse is minutes per revolution, and then we convert it to seconds using unitary arithmetic. I think this is something, when you look at the slides, you will figure it. And the transfer time is, everything is the same, but you divide by the number of sectors per track, because you only want to read one sector. You don't want to read the whole track. So you divide it by the average number of sectors per track. So this is a typical, so if we give you all this, you should be able to use the formula to calculate the access times. So the seek time here is 9 milliseconds. 4 millisecond is the rotation, and the actual transfer time is 0.02 millisecond. Now it turned out, what does this tell me? That the majority of the time is spent in seeking and rotating, in rotation and in the arm movement. Okay, so if I'm accessing sectors that are next to each other versus I'm accessing sectors that are in random locations, which one is faster? So when you have a storage device, and this is true for other types of storage devices, we say that sequential accesses, sequential is much, much better than random, okay? This is an enduring idea in computer systems and storage devices. Sequential accesses are faster than random accesses, remember that. And the reason for that, I think, is clear. ARM is a mechanical component. Moving it takes a long time. Rotating the disk takes a long time. The actual sector, reading the actual sector, transferring information, 512 bytes, does not take that long. So sequential is much, much better than random. And that's where storage devices, disk drives are very different from main memory, physical memory, RAM. So this complicated geometry is exposed to the operating system as a sequence of logical blocks, okay? Otherwise, the operating system has to do too much work figuring out which platter, which sector, which blah, which blah. The disk exposes all its sectors as a sequence of blocks. We call them B-sized logical blocks. And then there is something called a disk controller. You might have heard of, there's a disk controller. There's a controller on disk that do the translation between logical blocks and physical sectors. So these translations are really important in our systems. Translation from logical to physical sectors. And the controller has to figure out three things: the surface, the track, the sector. To make the life of operating system easy and system software easy, the disk controller exposes a logical number of blocks. So the word logical we'll use a lot in this course. Logical control flow were being mapped to physical control flows when we were abstracting, when we had the process abstraction, when we were creating the process abstraction. And now we are mapping logical blocks to physical sectors. Okay, so this is something the disk controller does. Okay, so now this is our complete picture. Recall that I was telling you that the CPU has direct access to memory. Okay, now we will see how this is different when you are accessing storage devices. There is an I/O bridge, there is a memory controller, but you have an instruction and you place the address on the memory bus and you get something from memory. So now we have the I/O bus here that is connected to the I/O bridge. So I/O bridge is now listening from the CPU and communicating with main memory and the devices that are attached to the I/O bus. So we have our USB controller with mouse, keyboard, graphics adapter, monitor. This controller actually is a communication channel between the I/O bus and the disk. And there are different communication protocols. You might have heard of SATA. SATA, anybody? SATA, SCSI, these are all communication protocols that the disk controller, I forgot how this SATA, SCSI. We don't have to go to that level, but they have different speeds and different protocols. Some protocols are faster than the other. Okay, so we have the system bus, the memory bus as before, and we have the I/O bus. And let's say the CPU initiates a disk read by writing a command. So you've already done memory mapped I/O, right? In 2300. In memory mapped I/O, some addresses in the address range are reserved for communicating with I/O devices. And we call each of these addresses as an I/O port. We call it an I/O port. So there is a special address that is reserved for communicating with disk, let's say anything, doesn't matter what it is. And when the I/O bridge sees that address, it knows, oh, this is an I/O port. I don't need to go to memory. I need to go to some I/O device. This is memory mapped I/O. The CPU generates an address, and that address is reserved as an I/O port for communicating with I/O devices. Other addresses in the range are for accessing main memory. Now, the CPU initiates a disk read by writing a command, logical block number, and destination memory to a port associated with the disk controller. So these are special, these are store instructions, but the address tells the I/O bridge that this is, I need to communicate this information to the disk controller. And the CPU communicates the command, logical block number, destination memory address, whether or not the disk controller should send an interrupt after the transfer is done or no, and a bunch of other information is sent on this I/O port, which is a special address reserved for communicating with the disk controller. The problem is, and this is where the lack of direct access will become clear, CPU can do a lot of work in 10 milliseconds. Once again, imagine if the CPU would wait for 10 milliseconds for the disk to respond. In the life of a CPU, that's eternity. 1 gigahertz, 2 gigahertz processor can execute hundreds of millions of instructions in this time. So what happens is that the disk controller, using this channel, places the sector 512 bytes in memory. And this is called direct memory access, or DMA. This is a DMA transfer. The CPU is not involved. After sending the commands on the IO port, which is a special address that can be accessed using normal instructions, the CPU goes doing something else using a context switch. The CPU context switches to some other process. Hey, I don't want to wait 10 milliseconds just sitting there waiting for disk, arm movement and all that. I'm going to do something else. I'm going to run process B. And this transfer happens now between the disk and memory. Now, how will the CPU find out eventually that the transfer is complete? What can the disk controller do to tell the CPU, hey, I need your attention? Interrupt, right? Interrupt. And finally, the disk controller interrupts the CPU. Hey, your transfer is complete. And the kernel will now switch, context switch to the process that initiated the disk transfer, because now the data that process needs is now in memory. This is not a direct access. This is an indirect access through DMA. The CPU is doing something else, and the data arrives from disk to memory, and then between CPU and memory, right? There is no such path here. And this is an interrupt. So as long as you're doing computation over something in memory, things are very fast. The moment you have to go to an IO device, you have to go through all this. IO ports and sending commands and DMA and then all that, context switches and all that.
How does the operating system know
When the interrupt arrives, there's a table that the kernel maintains, and it checks, which process is waiting for. And there is other information with the interrupt that the disk controller sends. There's an entire protocol. So which processes are waiting for something from disk, and then the kernel has information about, which process asks for sector number this and all that, and this file address and all that, and it matches all of that to. So typically, it's not just an interrupt; it's a lot else, right? With the interrupt, the disk controller sends more information. This sector, this file, this blah, right? Okay, so this was all about disks. At this point, we know that accessing the disk is not the same as accessing random access memory. There's a bit more involved. We know that sequential accesses are faster with storage devices than random accesses. And what are the sources of overheads when accessing a disk? So solid-state disks are an improvement over disk drives. There are no moving parts. This is flash memory. You all use USB flash. It's everywhere today. I just want to have a couple of slides about the internal organization. So once again, flash memory is divided into blocks, and each block is divided into a number of pages. Each page is typically 512 kilobyte, 4 kilobyte. and blocks have a number of pages. The problem with flash memory is that it's non-volatile memory, and you need to erase. Erase means clear, set everything to 0. You need to erase an entire block before you can start writing. So pages can be written only after the block has been erased. So if you take a block that has been erased using a special technique, everything is 0, you can start writing your pages only once. You can write each page once. If you have to overwrite a page, you have to copy all the data to a different block that is erased. You have to erase the block and then write again. So erase, write. If you have to overwrite a page, copy all the pages somewhere else, erase, write. As long as you are doing sequential writes, everything is good. The moment you start doing random writes and rewriting certain pages, once again, random accesses become terribly slow. The equivalent of disk controller here is the flash translation layer. And this is, first of all, it translates logical block addresses to physical pages, whatever the disk controller was doing. The other thing it does something smart to minimize the number of erasures. So you don't have to erase so much. There's a lot of techniques today the flash translation layers use to minimize the number of times you have to erase a block. We won't get into that. But basically, every time you have a write, you can do something special. You can remap that page to an already erased block, stuff like that. The technology that is used in flash memory, typically after 100,000 writes, the block wears out. Wear is something, wears out mean it is no longer useful. Wear is, something that is no longer useful. It's something. The way the technology works, you have to erase things, you have to write things. Those are very stressful operations for the technology that is used in flash. And wear out is something that is not relevant to disks, that is not relevant to RAM, but these devices don't last a long time. After 100,000 writes or something, the block is no longer useful. And one of the things that the flash translation layer does is wear leveling. It tries to level all the writes across, spread them out across the device to different pages. All right, so sequential access is still faster than random access, and the reason random writes are slow is because erasing a block takes a long time, and modifying a block page requires all of the pages to be copied. And here are some bandwidth numbers. Sequential write throughput is much higher than random write throughput. Throughput is how much you can write per second. Latency is how long does it take to access a single sector or single block. There is this distinction between latency and bandwidth that is important. This is bandwidth. How much can you do per unit of time? So I'm just showing you that once again, even though we have a smarter or sort of semiconductor technology, which has no moving parts, we are still stuck with this property that sequential accesses are faster than random accesses. So this is a gap between, if we think of in terms of nanoseconds, this is the gap between CPU and DRAM. So let's pick 2015. So after 2003, this graph on the x-axis is year, and on the y-axis is nanoseconds, 1 billionth of a second. For CPU, it's showing the cycle time. How big is a cycle? And typically, the CPU can do some work in a single cycle. It can execute one instruction in each cycle. And this is the SRAM latency. So SRAM, so after 2003, they are dividing cycle time by the number of cores, because after 2003, we started to build multi-core processors where each processor has many cores, because we could no longer increase the frequency due to power limitations. So you can see that the gap between CPU and SRAM is not that much. Between DRAM and CPU, there is still a lot of gap, and between SSDs and disk, the gap is really, really very wide. But the real capacity, if you want a capacity, that you don't get capacity from SRAM. SRAM is really expensive. If you want capacity, you have to go to DRAM. If you want speed, you want SRAM. Okay, so now we are going to look at how we build computer systems to bridge this gap between different technologies. So we want all of them. We want the capacity of these devices. We want more main memory, but we want the latency of SRAM. We are going to understand the idea of locality. What does locality mean? And how we bridge this gap between a very fast CPU and very slow technologies, storage technologies, is using locality. So programs tend to use data and instructions with addresses near or equal to those they have recently used. So programs, if we observe how programs are written, they tend to use data that is next to each other. Or at least we should write programs, or we can write programs in such a way that they use data that is next to each other. If you think of how we access arrays in a for loop, we are accessing elements that are next to each other. Temporal locality is when you bring something from memory. Memory is slow. We know that. When you bring something from memory, you use it again and again and again. So you have a variable called sum, and if you bring it from memory, if you use it again and again and again, if your program uses it again and again and again, we say that the variable sum has temporal locality. Temporal means in time. Temporal means in time. So this variable sum, if time is on the x-axis, and if there are x-axes, if the CPU accesses the variable sum 3 times, we say that this variable has temporal locality. In time, it is accessed again and again and again. So it was worth bringing it from memory, even though memory is slow. Spatial locality is when you access one item or object in memory at address A, and you then access something that is placed next to that address, we say that there is spatial locality. Locality in space. When you access something placed here, you access something placed next to it. So spatial locality is items with nearby addresses are referenced close together in time, and temporal locality is recently referenced items are referenced again in the near future. So temporal locality in time and spatial locality in space. Okay, let's do an example to figure out what this really means. So the variable sum here, does it have temporal locality in this code? In time, we access sum again and again and again in a for loop, right? Does it have spatial locality, sum? Does sum have spatial locality? Actually, we don't even know what is next to sum in memory. We know nothing about it. Sum is just one variable. We don't know what is next to it. We're just accessing sum. Okay, the array A, does it have temporal locality? Yes or no? When we access an element AI, do we access it again? So you have to be careful here, huh? Locality could be tricky to figure out. When I access element AI, I don't access it again. There is a for loop. I access the next element, not the same element. Does A have spatial locality? Okay. So because we are accessing the array elements that are placed next to each other, 0, 1, 2, 3, 4, we call it a stride. Stride is, how far you're jumping. We call it a stride 1 reference pattern, right? Stride 1. If I was accessing elements like this, what would I call it? Stride 2. So the bigger the stride, the less the locality. Stride 1 has very high locality, spatial locality. You see where it is going, right? What we are going to do is, when we access memory, which is really, really slow, we are not going to bring one object. We are trying to bring a lot of objects, hoping that the programmer has written the program in such a way that there is very high locality. And then we are going to bring things from slow DRAM into fast SRAM, which is on the CPU, in blocks. Okay, we'll do that in a minute. Let's try to keep exploring locality. Okay, being able to look at the code and get a qualitative sense of its locality is a key skill for a professional programmer. If your programs have high locality, we can build systems in such a way that that locality leads to very good performance. And we don't have to access slow memory all the time. Okay, let's do this. Does this function have good locality with respect to A? Okay, remember how arrays, two-dimensional arrays, are laid out in the memory system. What do we call it? How C lays out arrays in the memory system. We discussed it in the first two lectures, row major order, right? Does anyone remember what it is? Rows are next to each other, okay? The other way we can do it is columns are next to each other. We don't do that. In C, rows are placed next to each other in memory. So if I have an array and the rows are placed next to each other, I'm just going to put this in the middle to show different rows. And the index for the row is I equals 0, I equals 1, I equals 2, and the column index is j equals 0, j equals 1, j equals 2. If this is how your two-dimensional array is placed in memory, does the array has good locality here. Does it have good spatial locality? The rightmost index, okay, I'm going to say it in a fashionable way, has very high entropy. Entropy is when something changes a lot. Anyway, the rightmost index is changing rapidly, meaning the way my array is laid out, I'm accessing this, and then I go back to the outer loop, and then this, right? Good spatial locality. As a programmer, what can I do to destroy the spatial locality? I'm a terrible programmer. I do weird things. What is the
You switch the forward.
right? If we switch the for loop, what happens? If we say j equals 0, j is less than blah, m, sorry, let me go here. J equals 0, j is less than j, and j is now this, and I is this. What's happening here? So this is my row, and this is j. What is the first access? A, 0. What is the next one? Where is A1, 0? Stride? Yeah, all right. So now you understand spatial locality in programs. And this was an exercise in your lab 3 as well, I think. Did anyone finish that? The struct of arrays and arrays of structs? Okay, this is homework, but can you do it quickly? Can you predict if you have three for loops and you have a 3-dimensional array?
Pretty sure that code is wrong anyway. A is m by n by n. And it's like iterating in the wrong order for it to be m by n by n.
Wait, you're talking about this or this?
Yeah. So it's size n by n by n, but the indices are n and n and n. Only for I goes to n instead of n.
Note for self, fix this. Okay, we'll do it in homework. Sorry. Okay, so how do we exploit locality? Once again, the problem is, remember this chart here. The gap between the CPU speed, if you don't forget the rest of the graph, the gap between SRAM and CPU is small. The gap between DRAM and CPU is very, very large. And we need to bridge this gap somehow. So fast storage technologies cost more per byte. So SRAM is very, very expensive and have less capacity, require more power. Well-written programs have good locality. So what we do is we actually do something, we have a hierarchy. We don't have one level of memory. We have multiple levels of memory. So we have the registers that are very close to the processor, but you access the registers using instructions. What you place there is the compiler figures it out at compile time. Then you don't go directly to DRAM or main memory. You have multiple levels of caches, which is SRAM technology, and it is on the CPU die. It's on the same die as a CPU. And this is small amount of SRAM that we place close to the CPU. So when we bring something from DRAM, we don't just bring a byte, we try to bring a block. 64 bytes is very typical. The reason we do that is to exploit spatial locality and temporal locality. And we don't have one level of cache, we have multiple levels of caches. You go down, the capacity increases. You go up in this pyramid, capacity decreases. You go down, capacity increases in this direction. This is more capacity. And cost increases in this direction. So everything here is very costly. So you can't have lots of it, okay? Everything here is cheap. The down you go, the cheaper you get. So you can have lots of capacity at the bottom, but it's very, very slow, right? So now we are trying to bridge the gap. So cache is a small, fast storage device that acts as a staging area for a subset of data in a larger, slower device. Okay, so the basic idea is caches are everywhere. You can have a cache between any two levels. You can make main memory a cache for disk. You can have SRAM cache for DRAM. It's a very general idea, but let's explore it in the context of SRAM cache. Let's say I have this CPU die, and I know that memory accesses are too slow, so I'm going to put a small amount of cache, SRAM cache, inside the CPU. Before I go to memory, I will check the cache first. And if I find what I want in the cache, I won't go to memory. And this will save me a lot of time, okay? The way it works is cache at level K stores a subset of information or data from level K+1. Okay. So here the cache has block 8, 9, 14, 3, but memory has all these other things. So, and data is copied in block-sized transfer units to exploit spatial locality. The expectation is that if we bring lots of information, then the slow access, the overhead of slow access is amortized, because if the program has spatial locality, we will need all of the things we bring. So there is a request for block 4. We transfer the block to the cache. And next 10, okay, there's something called a cache hit. When there is a request for 14, you don't go to memory. You look in your cache first. And if the block is in the cache, it's a cache hit. Now there's no need to go to memory. If the block is not in the cache, it's a cache miss. In this case, you need to go to memory, and you need to do what? What do you need to do now? Bring 12 to your cache. Now, when you bring 12 to your cache, you need to decide where to place it and which block to evict. You need to find a victim block. So 12 is fetched. So the placement policy and replacement policy determine where you place a block and which block is the victim. The most extreme policy is random. Do a random placement of the block and randomly pick a eviction candidate, a candidate for eviction. The problem is that if you randomly place a block anywhere in the cache, when you have to look up the block, you now need to spend a lot of time because it could be anywhere. So typically we restrict the locations where we can place a block. So our placement policy is more restrictive than random. Let's place it anywhere. We don't do that. There are three kinds of cache misses. Cold miss is when the cache is empty. If there is nothing in the cache and you need to access something, you have to have a miss. There is no way you can serve the request from the cache. So cold miss is when the cache is empty. Capacity miss is when the working set of a program phase is how much data is it accessing in that phase. So in the for loop that we looked at, we were accessing an array of size n. And if we call the for loop a phase of the program, we say that the working set is n data items, right? So programs have phases. There's a for loop, you're accessing an array, then there's another for loop, you're accessing something else. And we call it the working set. If the working set does not fit in the cache, we call it a capacity miss. So misses, you can remember 3C. Conflict misses, when you restrict the number of locations, each block from level k+1 can be placed, multiple blocks will conflict for the same location. So if your policy is that any block from level k+1 must be in block I mod 4 at level k. In this example, I mod 4, then 0, 8, 12 will all conflict for the block, the blocks here, this one. And 1, 9, and 13 will all conflict for. So conflict is when you restrict your placement policy. When your placement policy is not a block can go anywhere. When you restrict it, you end up with multiple blocks at level k+1 mapping to one block at level k. So we will not just see hardware caches that are inside the CPU. We will have software caches as well. Operating system maintains a cache called buffer cache. This will come up in your labs at some point. Then there is in your browser, there is a cache, web cache. Caches are everywhere. You observed how much overhead there is in accessing a disk, arm movement, rotation, this, that. So operating system is smart. If I bring some sector or if I bring some data from disk once, let me keep it somewhere in a cache in memory. Let me not go to disk for every access, and this works. And you will explore it in lab 6. So caches are everywhere. Well-written programs exhibit locality. As programmers, you are going to write code that has high locality. As programmers, you are going to write low-level system code such that the accesses are mostly sequential. You are going to keep these lessons in mind. You are not going to write code with random accesses all over the place. You're going to care about locality. Your software must be informed by the device characteristics from now on, okay? All right, so I had something, well, we do have time. Okay, this is all today. I don't want to bring device characteristics again in this course. This is not a course on computer organization. This is a course on system level software. So bear with me for 5 more minutes and we are done forever with arm movements, rotations, and all that. Actually, I might bring it up if we need it. So How does we want to look at a little bit more detail. This DRAM chip is a mystery at this point. You know, in all your coursework until now, we show you a block and we show you byte addresses, little Indian, big Indian, blah, blah, and move on. Let's explore a little bit more. This will help. So the way this DRAM chip works, this is a 16 into 8 DRAM chip. We call it X8 if you ever go to buy it. So there are 16 cells, and we call each cell actually the supercell. And each supercell has, in this case, 8 bits. There's an interesting lesson here that I want to convey. Now we organize physically the DRAM, this 16 cell as a matrix, and the address bits we have connecting the memory controller to the chip is 2-bit wide. Okay, what we do is, so this is 8-bit, so each supercell is 8 bits wide, and we want to read 8 bits at the intersection of second row and first column. So we first send what we call the row access strobe. Strobe is like a flash, just a quick signal. We send the row address strobe to, with 2 bits, we can access 4 rows. So we are accessing the, actually I'm saying second row, it's a third row, row address at index 2. After that, we send another strobe. Okay, we read the entire row in something called a row buffer. And this row buffer is actually SRAM. So even inside the DRAM chip, we are trying to exploit locality once again. So we have all these supercells in this row number 2, and we read all of them in the row buffer. If I want this cell, the 8 bits stored in this supercell, what do I need to do now? This is my column. This time I send a column access strobe. And I read the 8 bits. I send these to the processor. Now, but with this organization, what I'm trying to do here is, what I want to tell you is, you don't have a lot of pins. Pins are not free. Pins are very expensive. So these 2 bits that connect the memory controller to the DRAM chip, these are actual pins made of metal. And today, memory controllers are actually placed inside the CPU. So CPU doesn't have a lot of pins. It's a very, like, if you ever see a CPU, you don't have a lot of pins. You have to preserve as many pins as possible. So with this 2-dimensional arrangement, I have saved 2 pins. Now here I've saved 2 pins. On real systems, we end up saving many pins with this arrangement. So 2 things. First of all, the real translation of addresses is a little bit more complicated. We need row access strobe and column access strobe. Second thing, locality and caching is everywhere. Even in a DRAM chip, I have an SRAM row buffer, and my expectation is that if I'm sending this supercell this time, then next time, if I need to access, if there is a request for this supercell or this supercell, then I don't need to go to the DRAM array. I can serve the request from the row buffer or the SRAM that I have placed in my DRAM. Even disks have SRAM and DRAM. SSDs have SRAM, DRAM. Caching Locality is everywhere. Okay, so what we do in reality is when we want to get more capacity, we have many of these chips, and we have an array of these chips. Each of them generate 1 byte of a 64-bit word. Typically, for communication between CPU and memory, we don't send just 1 byte, we send 64 bits, because this is the size of our bit of our registers. This is what programs typically access, integer I, long, all this. So we don't send 1 byte, we typically send an entire word. And we combine these DRAM chips into an array. So here we have 8 DRAM chips, 8x8 DRAM chips. Each of them produce a single byte of a 64-bit word. Okay, I can skip this. Okay, so we're done with device characteristics. Now, from now on, in the labs and in the course, we will be using these ideas: locality of reference, spatial locality, temporal locality. You should look at the program and say, hey, I can do this rearrangement to exploit more spatial or temporal locality. You should be able to look at the program and say, hey, there's a lot of random accesses when I'm accessing an IO device or a storage device, when I'm accessing a file. I can do something really smart to turn all of these into sequential accesses. Okay, and we will keep exploring these ideas as we go. All right, thank you.
The Zoom lecture, Zoom recording for last week's lecture could be uploaded, because my friend,
It is uploaded.
it is up there.
Okay.
Yeah, because my friend said the echo recording, so the echo recording finishes 5 minutes before the hour, or before the end of the lecture. So, since we started 10 minutes late and we normally go overtime, he wasn't able to get all of that. Same with this, like, where, so like, let's